Welcome to Ask and Learn.
All right, so in this problem, we have two functions, f1 and f2, and they run from the reals to the positives, positive reals. And we also have that f1 and f2 are both big theta of g. All right, so by definition of big theta, this means that both f1 and f2 are big O of g, and they are also big omega of g. All right, so knowing this, we can consider constants c1 through c4 and k1 through k4, such that we have that f1, since it runs from the reals to positive reals, is going to be equal to the absolute value of f1. All right, and this must be less than or equal to c1 of g, right? This is due to being big O. Okay, so whenever x is greater than k1. And then we also have, by a similar argument, that f1 of x is necessarily greater than or equal to c2 of g. And this would be when x is greater than k2. We also know that f2 is less than or equal to some constant c3 times g, since c2 is also big O, and also that f2, since it is big omega, must be greater than or equal to some other constant, also times the absolute value of g, right? And this will be when x is greater than k3 and 4, respectively. And I skipped writing it, but due to these functions running from the reals to the positives, right, f1 is just going to be equal to its absolute value, and f2 is also simply equal to its absolute value here. Okay, so then we're just going to let k be equal to the maximum of all those other k's we had, right, k1 through 4. And then we're going to consider what happens when we add f1 and f2. So if we take the absolute value of f1 and add it to f2, again, due to these functions only having outputs in the reals, this is just equal to f1 plus f2. All right, and this, from the previous page, we know must be less than or equal to c1 of g times g plus c3 times g. Right, so this was due to their big O definitions. Great, well, we can combine C1 and C3. Right, so this is going to be C1 plus C3. It's the distributive property times g of x. And this will occur, of course, when x is greater than k. Well, by a similar argument, we can also get that the absolute value of f1 plus f2 must be greater than or equal to c2 plus c4 times the absolute value of g when x is greater than k. All right, well, if we just let's say c1 plus C3 be equal to D1, and if we let C2 plus C4 be equal to D2, then we get that the absolute value of F1 plus F2 is both less than or equal to some constant D1 times G. Right, so this means it's big O, and it's also greater than or equal to another constant D2 times G, which means it is big omega, and therefore it is big theta, right? So therefore, F1 plus F2 is big theta of G. Okay, well, so then that concludes the proof here, but it asks us one more thing, and it asks us, was it still true if they can take on negative values? So is this still the case if, say, F1 and F2 are functions that just run from the reals to all the reals and not just the positives? Now, this is not going to be the case. It's not true that it would be big theta, and this is because the steps where we had set, say, the absolute value of F1 being equal to that function output. And the same thing for F2 would no longer be true. Additionally, when we took the absolute value of the sum, right? So the absolute value of F1 of X plus the absolute value of F2 being simply equal to those function values would also not be true in the proof that we did. Okay, so it is not necessarily the case that if these functions can take on both, that it would be big theta. And so, for example, if F1 was equal to X plus 1 and F2 were to be equal to negative X, then F1 is big theta of X, and F2 is big theta of X. Okay, but if we take the sum, so now if we want to take F1 plus F2, we would get X plus 1 minus X, which is equal to 1. Well, 1 is not big theta of X, right? So there's